So today we will be basically addressing two problems. That's it. Two probability problems, and hopefully using these problems we will be covering something called random processes. All right, so what is the problem? The problem is the following. So I start at 0, and so this is 1, this is 2, the real line. I flip coins. So if I flip a tail, I'll just jump by 1. If I flip a head, I'll jump by 2. The question is, what is the probability that I will hit any given number? Let's say, for instance, n. What is the probability that I will be hitting n, right? So jump +1 if tail, and +2 if heads. Then the question is, so this is the rule. What is the probability? What is the probability of hitting? Well, let's try something. Hitting n is equal to, say, 1000. What is the probability of hitting 1000? All right. Do you guys kind of, well, 1000 is a big number. So there's a chance we can jump over it, right? Because if I was at n-1 at any given point, and if I flip ahead, I will just jump over it. So what do you guys think? What could be that probability? This is my question, right? So the question is, what's the probability that I will land on n equals 1000? All right, so there is, some people think it might be 1/2. Okay, that's a good guess. Let's go ahead and try the easiest idea that comes to mind. Let's start with small numbers for n. 1000 is way too big. Let's create a chart. I don't know, so n here and p of n here. All right, and let's start with n is equal to 1. What is the probability that using this I will hit a 1? Yes, I think everybody agrees, right? There's a 1/2 chance we will be really hitting a 1, because the game starts at 0, and at each point we just flip a coin and we keep processing rightward. Because our goal is to see if we will be landing on 1 actually, there's a 1/2 chance I will be flipping a tail, and there it is. In fact, what I can do is the following. I'm starting at, I can create this chart if you guys want. I can start at 0. There's a 1/2 chance I will flip, I will land at 1. Why? Because I'm flipping a tail. And 1/2 chance I will be flipping a head and then landing at 2. So that makes sense. How about 2? N is equal to 2. What are the chances that I will be landing at 2? How many ways can I end up at 2? Can you write down the coin flips that I need to land at 2? Yes, yes, good. Either I need tail, or just a single head. Anything else won't work. In fact, the following, if I extend this picture, so anytime I make a left means tail, right means head, okay? So if I were at 1 previously, in the next move I can end up at 2 if I flip a tail, or I can end up at 3 if I flip a head. If I was at 2 previously, I will end up at 3 if I flip a tail. I'm joining those two vertices. And then I will, being at 2, I can further flip ahead, after which I will end up at 4, actually. You guys see that? So therefore, when we are addressing the question of what is the probability of reaching a 2, there's 2 different ways we can reach a 2, either through here or through here. You guys see that? So the probability of, I can either go to 2 directly. So this probability is either in my first trial, I flip a head, or in my first trial, I flip a tail, followed by a tail first, followed by another tail, 2 tails in a row. And indeed, if you add up these things, 1/4 plus 1/2 would be 3/4. Okay, we are going good so far. How about 3? I think by now you guys see the pattern, right? I can just keep extending this picture. Let's do it. So I can flip another tail. When I was at 2, I can reach 3. Or I can flip ahead, after which I will reach a 4. If I was previously at 3, I can either flip a tail, after which I reach 4, or I flip a head, after which I reach a 5. The same thing from 4, either a tail or a head, and I can end up at these two. So the question is asking to the probability of reaching a 3 ever. These are pretty much the only ways to reach a 3. So all I need is, okay, can you tell me the coin flips that I need as a result to reach a 3? That's right. So you guys already calculated. Yes, 5/8. Well, either I have 3 tails in a row, 1, 2, 3, or I can have a tail followed by a head, or a head followed by a tail, right? That's pretty much it. So, well, and you can easily calculate the desired probabilities. In fact, because we keep moving 1 and 2, yes, you guys suggested that we should use binary, not binary, 1s and 2s. So what you're saying is, I can represent tail as a +1 and head as a +2. In a sense, we are trying to reach the number 3. Last week we did partitions. How many ways can you partition 3? By just using 1s and 2s. You can either write it as 1 + 1 + 1, or you can write it as 2 + 1, or 1 + 2. But the probabilities here are bigger, right? The probabilities here are, because you have only 2 coin flips, 1/4 each. So 1/4 + 1/4 is 1/2, and the probability of this one happening is 1/8. So 1/2 + 1/8 is 5/8. That's pretty cool. And we can keep going on like this. Did you guys calculate for 4? How can I reach a 4? I can get to a 4 by 1, sorry. Or I can have what else? Oh, you guys are good. I can have a 2, 2. What else? 2, 1, 1. Or any ordering of these, right? So therefore, yes. So the individual probabilities as a result, this one will be 1/16. This one is 1/4. Each of these, there are 3 of these, is 1/8. So 3/8 plus 1/4 plus 1/16. And I'm assuming you guys did the calculation correctly. It is 11/16. Now the question is not asking for n is equal 1, 2, 3, 4. It's asking for n is equal to 1,000. That's decidedly a big number. Wow, so you guys already have made some calculations. Okay, let's go back to the heuristics. Is that what you call? Intuitively, what should be the answer for a large n? What should be the answer for a large n? Intuitively. For instance, what if we had 100 coin flips? So intuition. I'm using some because if you don't have intuition, sometimes you solve a problem, but you need to make sure that it passes the smell test, right? Okay, good. So intuitively, suppose that if you had 100 coin flips, how many heads and tails? 100 coin flips. I mean, in average, yes, 50-50, right? We were expecting 50 tails and 50 heads. So after 100 coin flips, our bug, or whatever that is, the frog, let's say, the frog will have reached, each of these will contribute a 1, so 50 plus 50 plus, each of these will contribute a 2 plus 100. We would have reached the number 150 in average, but we did how many, we visited how many integers until we reached 150? How many integers did we visit after 100 coin flips? Yes, we visited 100 of the 150 numbers. By that time, we reached this number, but along the way, we visited 100 different numbers. That kind of is a good heuristic, suggesting that the desired probability as n goes to infinity, probably P of n is 2/3, or in this example, well, in this example, 100/150. So that's roughly 2/3. That's a good heuristic. Do you guys agree? So whatever formula we end up getting, it should give us a formula which is extremely close to 2/3 for large n. Do you guys agree on this, what we did? Yes, the answer should be close to 2/3. And indeed, if you inspect these numbers are approaching 2/3, it seems. Now, this is not a good way to approach this problem, right? So this table, I mean, it's nice if, for instance, if you are taking the AIME or the AMC10, the question is if n is 10, I think this is doable. You can go all the way up to 10. But if in the case of 1000, this table won't lead you too far. So you need some additional machinery, right, to help us. And probably we can resort to this idea again. Just let's revisit the very first attempt. Okay, so let's go back to that table. Actually, let me just do it next to it. So I still have some space over there. I'll just move my chat box. So suppose that we started at 0 again. So if we flip a tail, we end up at 1. If we flip ahead, we end up at a 2. Now the question is, if you end up at 1, the goal is to reach that number n, right? So how many steps is remaining until we reach there? Versus if we land at 2 with 1/2 chance, so there's a 1/2 chance I will land at 1, after which I need n-1 more steps. Do you guys agree that this is p sub n-1 left? Yes, indicate yes. And then if you, in the first step, if you reach by the end of the first step, if you flip the head with probability 1/2, you reach 2, and there is, you still need to go all the way up to n. But there is only n-2 steps left. So this is really the probability of p sub n-2. Do you guys agree? So therefore, we can write it out in a recursive form as well. So Pn, in a sense, is equal to 1/2 chance we will end up at the node 1, after which the desired probability of is p sub n-1, and 1/2 chance, oops, let me just move this a little bit, 1/2 chance we will end up at 2, after which we need to go n-2 more steps. But the desired probability, we decided to call it p sub n to move a distance of n and hitting that number n itself. So therefore, that's it. We want to solve this recursion. And by the way, we already calculated initial conditions, right? So we already know p1 is 1/2 here. Do you guys agree? So p1 here is 1/2, and p2 here is 3/4. And that's pretty much it. If we know, if we have some good high school algebra skills, you should be able to solve this recursion, pretty much solving some difference equations, right? But let's not try to resort to that. I know some of you guys already know how to solve it this way. I'll try to make it simple and just use some simple tricks to solve this recursion, okay? So we'll have more fun doing it that way. Oh, by the way, let's just test if this recursion works, right? I forgot to test it. For instance, P3 here is 5/8, right? Whenever you create a recursion, it's always customary to test it. Let's see if it passes our test. P3, if this recursion is correct, is 1/2 of P2 plus 1/2 of P1. And sure enough, 1/2 of P2 is, let me move a little bit more. So 1/2 of P2 is 3/4, P1 is 1/2, and does it work? 1/4 plus, or 2/8 plus 5/8. Yes, it seems it works. That's good. So we are pretty confident that this is the right one. So that's pretty good. All right, so now let's try to guess this sequence, right? There are multiple ways you can do it, right? One way would be to just guess the form and then use induction probably, right? But if you guys want, we can do the guessing in 2 steps. We can do the guessing in the following way. I can just try to guess just the numerators actually. How about that? Let me just change my color. So how about the numerators only? The denominators is very easy to guess, right? The denominators are just 2 to the n. Do you guys agree? So what I will do is Pn, I can guess it, okay, let's write it in this form. B sub n over 2 to the n. Can you tell me what are those B sub n? So B sub 1 is just the numerators. B sub 1 is 1, b sub 2 is a 3, b sub 3 is a 5, b sub 4 is an 11. Well, using this recursion, if this is correct, we can even find b sub 5 and so on, right? B sub 5 would be, well, p sub 5 is just the sum of these two divided by 2, right? The sum of those two divided by, so 5, 8 plus 11 over 16 divided by 2. 5 over 8 is just 10 over 16 plus 11 over 16, that's 21 over 16 divided by 2, 21 over 32. So b5 is 21. In a similar way, b6 would be, b6 is what? Can you guys tell me what b6 is? Just the numerator. If you guys want, I can just write next to it here. So I'm just focusing on the numerators. Okay, so there you go. So numerator here was a 1, a 3, a 5, an 11. The next one we found it was 21. And the one after that, I think will come out as 43. B6 comes out as 43. Yes. All right. So what is the rule? Can you guys tell me a claim? What do you claim B and the progression of BNs are? What would be a rule? 11 goes to 21, 21 goes to 43, and so on. Aha, there's a couple of different claims here. Well, one of the claims I really enjoy, well, both of the, okay, so let's see if there's more claims. Okay, that's a good claim. Almost everybody got the same claim. I had a different claim. I thought it was easier. The other claim was easier, but I will follow your claim. Okay, fine. Okay, my claim was the following. I was claiming that as you go from one to the other, it is as if we are just doubling. Yes, 2x plus 1 and 2x minus 1. That's correct. So some of you guys already suggest we just multiply by 2 and add 1, and then multiply by 2, subtract 1, multiply by 2, add 1, multiply by 2, subtract 1, and so on. Wow, that's pretty good. So either one works. Okay, so let me go ahead and write that out. So we have two different claims. Claim 1, we claim that b sub n is equal to 2b sub n minus 1, whatever is the previous number, plus, I think it's minus 1 to the power n. You keep adding and subtracting 1. Oh yeah, please make sure to subscribe to our channel. Yes, we have a YouTube channel, and we will be putting all these videos as a depository over there. Yeah, make sure to yeah. Okay, this is one. But I really want to use the second one. Okay, so you guys, almost everybody prefer the second one. Okay, let's see if we can derive the second one. Remember that Pn was just equal to 1/2 Pn minus 1 plus 1/2 Pn minus 2, right? I can just substitute this expression over here, right? Here and here. So that will tell us that, well, b sub n over 2 to the n is simply equal to 1/2 b sub n minus 1 over 2 to the n minus 1 plus b sub n minus 2, so 1/2, sorry, 1/2 b sub n minus 2 over 2 to the n minus 2, right? And what? Well, I can multiply across by 2 to the n. So that will give me, so this would imply b sub n is equal to multiplying across by 2 to, yes, that was your claim, I think, right? Almost everybody made this claim rather than no one preferred claim 1. Okay, fine. So this is no longer a claim, right? So, well, it is a claim because we don't even know if this is true yet, right? But, okay, so this claim is a better claim, it seems. Claim 2. All right, let's follow this one, I guess. People preferred this one. All right, so how do you solve this recursion? It turns out solving this recursion is easier than solving this one, the one related to Pn. This one is actually easier. All right, let's do it. Our goal is to solve this recursion. Well, what can I do here in this recursion? I need to do one trick. Tell me a trick that can help me solve this. Okay, you guys are good. You already have the all right, so the trick is the following. I'm going to go ahead and add a number to both sides of this recursion. Which number should I add to both sides? Or not an actual number. I will add something to both sides of this equation. What should I add? Yeah, go ahead, ask the questions. I'm following the chat box. You can ask it to each other. Okay, you guys can go ahead and add, I'm going to add b sub n minus 1 to both sides, okay? All right, so if you add b sub n minus 1 as well, check what happens. B sub n plus b sub n minus 1. Why would I do that? 2 times b sub n minus 1 plus 2 times b sub n minus 2. Why did I do that? I can factor out the 2 if you want. Okay, let's just go ahead and factor out that 2 over here. So I took that 2 out. What is the benefit of this? Ah, Darren, you're good. Darren suggests, let's describe yet a new variable, c sub n. Holy, we started with p sub n, then we went to b sub n, now we have c sub n. Let's call c sub n as b sub n plus b sub n minus 1. So as a result, we have, this one is just c sub n equal to 2 times, this one is c sub n minus 1. So c sub n is 2 times c sub n minus 1. And besides, because I know the initial conditions for the, oh, I forgot to write that down. Okay, let me write down the initial conditions for b. So we already know that b sub 1 is 1 and b sub 2 is 3. So similar, as a result, if c sub n is this, then necessarily c sub 2, I need a 2. So c sub 2 is b sub 2 plus b sub 1. That's just 3 plus 1, that's a 4. C sub 2 is just 2 squared. But hey, C sub n, so C sub 3, what is C sub 3? It is 2 times C sub 2, which is 2 cubed. C sub 4 is 2 times C sub 3, which is 2 times 3 to the cube, 2 to the 4. So therefore, what's the closed form formula for C sub n? So as a result, so the solution to this recursion here is, yes, 2 to the n. Therefore, this implies C sub n is equal to 2 to the n. Holy. So, and we can automatically remove C sub n now, right? Yes. Let's just get rid of C sub n now. So what I can do is here, let me change the color again. Here I can replace this C sub n here with 2 to the n. Holy, we haven't seen this even. This is yet a third claim. Look, earlier we should have seen this before. So 1 plus 3 is 4. It is 2 to the 2 squared. 3 plus 5 is 2 cubed. 5 plus 11 is 2 to the 4. Holy, there is yet so many more probably recursions, like patterns that is hard to see, right? That's the nice thing about math. You just keep diving in, and nothing is I mean, you are not losing time. Even if you go like astray, you will discover a lot of good stuff. All right, so C sub n is 2 to the n, and as a result, we replaced it here. Now this is our new recursion that I want to solve out, right? Well, we can do a quick trick. Remember our nudge, was it nudge? Where was it? Oh, here. Remember for n, as n goes to infinity, we were suggesting that the answer should be very close to 2/3. Let's see if our progress so far has paid off. So for instance, starting with this recursion, let me just carry it over here again. Okay, so I'm running out of space. So we have 2 to the n is equal to, what should I do here? How can I go back to P sub n here? What should I do to go back to P sub n? What should I divide by? So let's go ahead and divide by 2 to the n. Let's see what happens. If you divide by 2 to the n, guess what? 1 is equal to, why did I divide by 2 to the n? Plus b sub n minus 1 over 2 to the n. Oops. Hey, look at that. This is what? This is p sub n, right? And the next one is 1/2 times p sub n minus 1. Holy, we didn't even see that coming, right? Guys, huh? Yeah. Now, if this thing has a limit, And you might wonder if this, wait, yeah, you know, nobody challenged me early on. How do we even know that this has to have a limit? That's a good question. Does it even have a limit? I think it should have. Huh? So, but okay. So let me explain why I think this thing should have a limit, the Pn sequence, and then I can go to check the limit. So remember the desired probability P sub n is equal to, well, it seems when you go back all the way up, it is 1 plus, sorry, 1/2 plus 1/4 plus, how did we got the 4? We kept adding, right? We keep adding smaller and smaller numbers. All right, so, but I think it is reasonable that it should have, okay, so it should have a limit like we explained. Okay, I think I gave you the heuristics, right? So, okay, so don't worry about so if you call that limit as n goes to infinity as of P sub n as P, now guess what? As I take the limit as if n were to go to infinity, then we have 1 is equal to, if n is very big, like 1000, that would be very close to P. That would be 1/2 times P. Aha. And that is simply, so this would give us 1 is equal to 3/2 P, which implies P itself is 2/3. So at least I'm in the good, I'm in a good direction here. That's pretty good. All right, so forget about this. All right, so so that would be the limit. N goes to infinity here, n goes to infinity, and yeah, so that's a good thing that reinforces that we are doing a right job. Now let's finish this thing, okay? So because it's probably we need to go to the next question. So let's finish solving this thing now. So where are we here? We have okay. So let's start with this thing. All right. So I want to start with this thing. And let's actually, no, I don't want to start from that. Let's go back to our recursion. Oh yeah, this one. Okay, let's try to solve this. Okay, let me carry it over here one more time. So b sub n plus v sub n minus 1 is equal to 2 to the n. And I will do the following. I think, so I want to solve this, right? So I want to solve this recursion. And I claimed it is easy to solve this one for the following trick. I will keep writing it like this: b sub n minus 2, just substitute wherever you see n, substitute an n minus 2. So this one would be n minus 3, 2 to the power n minus 2, all the way, guys, come on, I need more civilization. You can go all the way up to b sub 2 plus b sub 1 is equal to, I think, 2 to the n minus 2. All right, so what should I do here to solve this? What do you guys think? I can't just add these equations. That won't work. Yeah, one easy way to solve this is, okay, so one easy way to solve this is you can multiply by +1, minus, plus, minus, and so on. The reason is the following: if you were to multiply plus, minus, these two will cancel, those two will cancel, and then so on. It will cancel with the next one, this one will cancel, and do you guys see that? So that's pretty good. You might wonder, what is this one? This one is, I think, minus 1 to the power 1 here. You can think of this as minus 1 to the power 2. It is whatever we are subtracting, that's what we are raising it up to. So here I'm multiplying this one by minus 1 to the power n minus 2. Do you guys agree? So if I were to add up these things, guess what I would get? I would have a bn left here and a b1, well, multiple. Okay, so we have bn plus minus 1 times b1, but b1, remember, was just 1 somewhere. We did it somewhere, I don't even remember. Oh yeah, here, b1 is just a 1. Aha. So that would answer, let me just move it over here like this. Yeah, so this times 1, so b1 is just a 1, is equal to, okay, here we begin. 2 to the n minus 2 to the n minus 1 plus 2 to the n minus 2 minus dot, 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 all the way up to plus minus 1 to the power n minus 2 times 2 to the power n minus 2 times. Now you guys need to solve this, but this is decidedly easy, right? Because now we have bn, I can just move this guy to the left-hand side and I would be done. All I need is to solve this thing, this right-hand side, which is, it turns out this is a geometric sum that you guys already know. Okay, so before I move that to the left-hand side, let me just manipulate the right-hand side. I can just factor out a -1 to the power n. Check this out. So what we left with is the following: -2 to the power n plus -2 to the power n minus 1, and so on. Do you guys see that? Plus -2 to the power n minus 2, all the way up to, plus, I think the last one would be -2 to the power 2, right? Wait, is this correct? I think it is. All right, so something like that. Sorry, this one is a square. So wait, 2 to the, no, I messed up. This one was a square. Sorry, guys. Sorry, this one is just 2 squares. Sorry, you were right. Okay, my bad. Okay, there you go. All right, that one was just a 2 square. All right, and now it's easy. I can add 2 additional terms here. -2 to the power 1 plus, even though they were not part of the thing, right? -2 to the power 0. And as a result, I need to subtract from it as well. -1 to the power n. I need to subtract -2 to the power 1 plus -2 to the power 0. Okay, and this is a finite geometric sum, which I know how to write it out as. So this is just -2 to the power n plus 1 minus 1 divided by -2 minus 1. -2 minus 1. And we still have this monster here, which is, what is this? 1 minus 2, so that's a -1. So this is a plus. So we have, I think, plus -1 to the power n. Okay, and this is, the denominator is a -3. So I can do one more step before I move this guy to the right-hand side. So that will give us -1 to the power n plus 1 over 3. And then I think what we are left is -2 to the power n plus 1 minus 1. And you guys can go ahead and move this guy to the right-hand side and boom. So you will get a closed form formula for Bn. And then you can plug it into Pn. Okay, let me write that out. So finally, if you plug it in, I think Pn comes out as, well, Bn over 2 to the n. And after you plug in everything, okay, so it's a messy expression like this: 2/3 minus 2 to the n and something here. Okay, so something, just a number which is a finite number, and that's it. And this is clearly, as n grows to as n grows, this thing will approaches 0, and finally you get the answer 2/3. All right, any questions about that on the chat box? People were a lot of excitement. Okay, so yeah, focus on the thing. I think this is a good way to attempt this problem. I know some of you guys got what's it called, a board. Especially if you already know, let me show you another trick here. If you already know the closed form formula, remember that this was our formula, right? I think some of you already know how to solve this. Divided by 2, so this is just 2 times Pn is equal to Pn minus 1 plus Pn minus 2. So this is a linear differential equation or difference equation. And the solution in general to these type of equations is the following. Pn is equal to, a particular solution would be c to the n, sorry. So what I can do is, if I substitute c to the n, I would get something called the characteristic polynomial, like this, where c is a number, c to the n minus 2. I can go ahead and divide both sides of this equation by c to the power n minus 2. So that will give me 2c squared is equal to c plus 1. And it is easy to solve this, right? 2c squared minus c minus 1 is equal to 0. I can factorize it. 2c, c is equal to 0. I think this one is a -1, this one is a +1. And finally, you would get the particular solutions -1/2 and 1. So therefore, the actual closed form solution will look like this: alpha times -1/2 raised to the power n plus beta times 1 to the power n, which is just a 1. So all we need now is to calculate alpha and beta. This is pretty much the way we would calculate the Binet formula for the closed form formula for Fibonacci numbers as well, right? We can make use of the initial conditions. Remember that P1 was 1/2 and P2, the probability of hitting 2 was 3/4, Do you remember that? So you can just plug these two into this equation twice, and you would get a system of equations for alpha and beta. So for instance, if you were to plug in 1 here, you would get 1/2 is equal to, plugging in 1, we would get minus alpha over 2 plus beta, and plug in 2, we would get 3/4. Oops, let me scroll down a little bit more. 3/4 is equal to, plugging in 2, alpha over 4 plus beta again, and boom. So you can solve this for alpha and beta. I think alpha comes out as what? 1/3, and beta comes out as 2/3. And as a result, the same, so you would get the same closed form as we did this one. So because if you substitute these two into here and here, so that would imply further that P sub n is equal to 1/3 minus 1/2 to the power n plus 2/3. Hey, the same 2/3 and the same like small number here. This is just a fixed number which is getting smaller and smaller. Because as n grows larger, because this is minus 1 to the n, minus 1 over 2. So as you take the nth power, that will get smaller and smaller. All right, so let me see if there's any questions so far. All right, so can we go to our second problem for today? The second problem has a little bit more bite. The second problem, we will learn about random processes, and in particular something called random walk. Random walk. So that's a very exciting subject, and it is widely used in physics, in finance. For instance, in finance, it is believed that stock prices follow what's called a random walk. So if you want to predict, if you want to invest in the stock market and you want to predict stock prices, as a mathematician, you can create a model, a random walk model of the stock price propagation, and so that way you can create a model and so on. All right, so my next question is the following. So this is the second problem, problem 2, and it is a very simple problem. Suppose that there's so many variations of this problem. Let me just ask the simple problem here. 1 minus 1. This is the real line. 2 minus 2. The question is, you start at 0, just like in the previous situation. This time, however, with 1/2 chance, you make a left. Suppose that if you flip a tail, you make a left. If you flip a head, or can I just write the individual probabilities instead? Otherwise, it will be annoying. Let's say 1/2 chance you will make a left, 1/2 chance you will make a right. The question is the following: what is, and let me, the probability if you start at 0, that you will ultimately hit 1? What is the probability you will reach 1? You will ultimately, you will ever reach the number 1? Question mark. All right, let's open the floor for discussion. Yes. What do you think that probability is? So at each move, you flip a coin. Suppose that you got a tail, you moved left, now you are at -1. You flip a head, you can go back, and then you flip another head, you go back. So what is the probability that, well, for instance, Aaron says it's 1/2. 1/2 is after 1 flip. We can reach 1 after 3 flips as well, right? Can we reach 1 after only 2 flips? After 2 flips, it's not possible. It has to be an odd number of flips, right? We can reach 1 after 3 flips. So for instance, we can reach 1 directly. We can have a head, and that's it. And we reach 1. Or we can have a tail followed by a head and a head. So the probability of this one is 1/2. The probability of this one happening is what? 1/8. Do you guys agree? Or, and is that it? Is that the only way? Or we can, for instance, we can have this. We can have a tail followed by a head, followed by a tail, followed by a head and a head. That one is 1/32 chance. So the question, and you need to add up all these probabilities. Or it could have been tail, tail, followed by head, head, head. Another 1/32 chance. So what do you guys think? What is the probability that you will reach 1? So far we have, anybody? 3/8. Well, 3/8 I can easily reach. Ultimately, do I ever reach 1? It's at least this and more. Okay, let's do the same thing. Let's create a binomial model again, just like we did in the previous question. So I start at 0. I can either, from 0, I can go to -1, or I can go to +1. 1/2 chance each. Once I'm at +1, I'm done. So let me keep track of the probabilities here. So this is 1/2 chance. I will reach 1 and I stop it there. Or if in my first flip, if I got a -1, I can keep flipping again. So I can reach -2 or 1, sorry, back to 0. And that's it. So we keep going on again, flip again. I can reach to -3, or I can go back to -1. From 0, I can go to -1, or I can reach 1. Oh, that's good. So that's another way to reach to 1. So how did I reach to -1? So to 1 in 3 steps. I did tail, head, head. Do you guys see that? Hey guys, come on. 1/8 here. Do you guys agree? Because we reached it in 3 steps, if you guys want, I can write it like this. 1/2 cubed. How about that? All right, I enjoy this game. Let's keep going. Let's do more. So, or I can go another step. Oops. Okay, so from -3, I can yet flip another tail, after which I go to -4, or I can make a head. Oh, wait. That's a -2, sorry. This one is a -2. Aha. Maybe good. Some of you guys are already seeing what's going on. From -1, I can go to 0. Okay. Or I can go further. I don't think I can reach after 4 flips. There's no way I can reach 1, right? Remember, I need an odd number of flips. Let's keep going. -5, -3. A tail here also will land me in -3. So let me put that -3 next to it. I can reach to -1 here, or from 0, I can reach to -1. Or I can reach to 1. Hey, that's another way to reach to 1. And what is the probability of this one happening? Can someone calculate it for me? So it would be something, because it's after 5 flips, it's 2 to the 5. How many ways can I get here after 5 flips? 1 way only? Let's trace it. I thought it was at least 2 ways, right? Look at that. We did at least 2 different ways here. Yeah, so it's counting the paths, right? Okay, so for instance, the green path is the following. I can reach it from here, or I can reach to it from the blue path. I can reach it from here. Do you guys see that? That's pretty cool, huh? So there's really 2. Oh, sorry, what am I doing? I basically did the same thing. Okay, sorry for that. Okay, sorry. I could reach it from here, 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 and here. There you go. Do you guys notice that really calculating the probability here, which is in this example 2/32? Huh? So really the probability is the following. It's as if I have a bucket here. I drop 1 liter of water here. The question is, how much will be accumulated in that node? How much water will accumulate in this node? How much water will accumulate in that node? We know that in this node, we will accumulate 1/2 water. This node will accumulate 1/, do you guys see that? 1/8. This one will accumulate 1/16, apparently 2/32. Do you guys see that? And we keep going. Okay, let's go one more. Let's see if you guys will see the numerator. We need to find a pattern for the numerator. Huh? Let's see who will be the first to see the pattern. So I can reach to 0 here, -2, -4, -6. I need to go one more. I need at least 7 steps. So -7. Here is a -5, a -3, -1. And finally, I can get to 1. Okay, can you tell me how many different ways we can reach to this? Nice. You guys are amazing. All right, so I'm counting the number of ways to reach there. Let's begin from top. So we start here, 1 way, 1 way, 1 way to reach here, 1 way to reach here, How many ways can I reach to that vertex? 2 ways here, right? From here, again, 1 way to here, because there's 1 way to get to here, and then 2 ways to get to here, either like this or like that. It means there's really 3 ways to get to here. There's 1 way to reach here, 1 way to reach here, and no surprise, 1 way to reach here and here, right? So that's why the numerators are, oh, sorry, this one wasn't 1, sorry. This one is a 2. This one was 2. As a result, this one is a 2, this one is a 2. Okay, do you guys see that? Exactly, so let's keep doing it. So 1, 4, 5, which means this one is a 5, this one is a 5. You are right, 2 to the 7. What will be the next one? This is a 9, a 5, a 1. What will be the next level? 1, 6, 14, 14. Okay, let me go 2 more, 2 to the 9. I need the coefficient of 2 to the 9. Oh gosh, I need to go quite a bit more, huh? What will be the numerator when I reach to 2 to the 9, huh? So, and then I will need 1 more. And then here I will reach another way to reach 1, 2 to the 9. What will be the number? Oh, nice. You guys are saying it's probably the Catalan numbers. Yes, that's right. So 28 here, 14 here, 27, 1, 1, 8, 27, 48, 42, and 14. Yes, 14 over 2 to the 9 of the water will accumulate over here, that much water. There's 5 over 128 water there, and so on. So I think this is a good one. Now the question is asking us to add all these numbers. These are different ways of ending up at 1. So do you guys see how we change this model into a binomial model, which is really a mechanics problem? Now it's like as if I'm dropping water from top and I'm trying to measure how much water is accumulating in these things here, nodes here, okay? Okay, so let's do it. So we will just add up these numbers. So P is equal to, and you guys are right, so the numerators are just the Catalan numbers. So the question that we want to address is 1 times 1/2 plus 1 times 1 over 2 cubed plus 1 times 1 over 2 to the 5 plus 1 times, sorry, what am I doing? I'm just sleeping again. Okay, so 2 times 5 times 1 over 2 to the 7 plus, what did you say the next one is? 14 times 1 over 2 to the 9, and so on. So you can make use of the Catalan number sequence if you want. The question is, remains, what is this number equal to? And technically this number is supposed to be less than or equal to 1. How can I add up all these numbers? Wait, do we have an answer already? The answer is 1 because, oh shoot, there are so many comments I can't even read, it's so fast. Okay, one of you guys suggested the answer is 1, but I couldn't have time to read his comment, sorry for that. All right, but the answer has got to be less than or equal to 1 because this is a probability. I wonder if, so basically what we are saying is we start at 0, 0, 1, this is the scale of the probabilities. So the first number is 1/2. So we go to 1/2. When we add the second number, it's 1/8, right? So which we will, by that time, we will reach 1/2 plus 1/8, which is 5 over 8. And then we will add the third term here, 1 over 16 more. So we will reach here. And then we will add the next guy, which is a tiny number. The question is, will it in the limit, will it approach a number here, x? So x has got to be less than or equal to 1 in the limit. So because this is an infinite sum, right? So we have an infinite sum where the numerators are the Catalan numbers and the denominators is the powers of 2's. Okay, so how do you solve this? We need to develop some machinery, and once we have the machinery, we will tweak the machinery in different ways. We will probably need something like we did in the previous step, right? Remember how we solved the previous question? Oh, what's a Catalan number and why there's a Catalan number in this picture? There was a question about Catalan number. The reason there's a Catalan number sequence showing up here is the following. Catalan numbers you would naturally, okay, so a quick check, Catalan numbers count the following. Suppose that you have an n by n grid. Well, actually, let's do a 4 by 4 grid, for instance. So suppose that you start at this point and your goal is to reach to here. So you start at 0, 0. You want to reach it to 4, 4. You are only allowed to go 1 right or 1 up. How many ways can you go from this to this is obviously 8 choose 4. We know that. Why? Because this problem is equivalent to choosing a sequence of 8 letters, 4 R's and 4 U's, and the total number of sequences is this. However, the Catalan sequence has an additional constraint. What is the constraint? The Catalan sequence says what? When you are constructing this, you are not allowed to cross the diagonal. You're not allowed to cross above the diagonal. So how many paths starting at 0, 0, you can touch these points if you want to, the main diagonal, you can touch it, but you have to remain on the diagonal or below. How many paths, basically, right? So that's the Catalan sequence. Why did it happen to be a Catalan sequence here? Because think about it. It is, for instance, let me do this. Let me use a different color, maybe gray. Look at this. It is a sideways. Do you guys see that this starting at 0, 0, for instance, here, suppose that we want to reach to 5, 5. So this is as if we are remaining, this is a square. My square here, I just rotated it 45 degrees and this is what I got, right? So I have so many paths that I can reach to that point, but I'm not allowed to cross the diagonal. This is the diagonal. It is as if there's a full table here and you are not allowed to use the full table. Do you guys see that? So that's why this is a Catalan sequence. All right, back to the thing. Okay, where was I? Oh, the limit. In the limit, we are claiming that this thing has a limit. This is an infinite sum. What is the limit? So let's call the limit is an infinite, if you will, table here that we have. Why don't we go back to the basics like we did in the previous problem? So we start at 0. In the first flip, either we go to -1 or we end the game at 1, right? If we are lucky, with 1/2 chance, we go to 1 and the game ends, right? So the desired probability, therefore, is the following. Okay, let me also at the same time draw the timeline so everybody is convinced what I'm doing. -1, 1, oops. Oh gosh, okay, hold on, 1. So there's a 2 here, there's a -2. Okay, so after the first step, either I will directly flip ahead, after which I am at 1. This will happen with probability 1/2, right? And that's it. Or with 1/2 chance, I will end up at -1. If I end up at -1, how far away am I from 1 now? How far away I am from 1? Remember, my goal, I'm trying to calculate the probability of reaching a 1. How far away am I from 1? I'm now 2 steps away from 1. Do you guys agree? So if the probability from going to 0 to 1 is x, obviously the probability of going from 1 to 2 is also x. Do you guys agree? So as a result, the probability, whatever is that number x that we are calculating, the probability of going from 0 to 2 is x squared. Do you guys agree? So therefore, the probability of going from -1 to 1 is also x squared. Do you guys see that? Where I got that x squared? And that solves it. Because it's 2 steps away from -1, right? So now we need to solve this, and that's it. So x is the answer. So we are claiming that this sum approaches to, well, I called it x now, right? So let me just change it. So we decided to call it x now. So this number is x, and I know that x has got to be less than or equal to 1. So what I did here is the following. Let me do it again. X, whatever it is, equal to, so x is the probability of ever reaching 1, right? So either I can reach 1 in 1 step, or in my first step, which happens with 1/2 chance, I will end up at -1. Once I'm at -1, I'm 2 steps away from 1. Because I'm 2 steps away, in 1 step, if the probability of reaching to 1, when you are 1 step away, is x, then when you are 2 steps away to reach to 1, it should be really x squared, the desired probability, x times x. All right, so now we can solve this easily. Multiply it by 2, x squared plus 1 minus 2x is equal to 0, meaning x minus 1 squared is equal to 0. Aha! X is equal to 1. You are right. Some of you guys early on suggested that y is x squared multiplied with 1/2. Oh, okay. So, okay, I start at 0. 1/2 chance I will directly go to 1. And I'm done, 1/2. Or 1/2 chance I will go to -1 times, once I'm at -1, what is the probability of reaching 1? Because 1 now is 2 steps away, 2 away. I know that whenever I am at 0, whenever I'm 1 away from the goal, the answer is x. Whenever I'm 2 away, it makes sense because I need to first reach 1, and then from 1, I need to reach 2. So the probability from 0 to 1 is x. The probability from 1 to 2 is another x. The multiplication rule, that should be x squared. So whenever I'm at -1 with probability 1/2, because we are 2 steps away, so it should take me a probability of x squared. And wow, so therefore, it is deterministic almost. So I will certainly hit 1, certainly. But by symmetry, I should also certainly hit -1 as well. If I'm certainly hitting 1, it means what will happen? It means I will hit 2 as well with probability 1. Do you guys agree? Because the probability starting with 0, ever reaching to 2 is x squared, right? The probability of ever reaching to 2 is x squared, but x squared is just 1 squared because we just found out that x is 1. So that's also a 1. So interestingly, every single point on the real line, whenever this is a random walk, whenever you are using a random walk, every single point on the real line will be hit, but not only hit with certainty, it will hit infinitely many times with certainty, believe it or not. All right, so do you want to go one step further than this? Okay, did I lose some crowd here? I might have. Okay, so let's, can I go one step further? Okay, good, let's go one step further. There's a couple of directions you can go from this point. One direction, okay, so let me show you one alternative. What if, okay, check this out. What if, so starting at 0, 1, 2, -1, -2. What if the probability of a right is a, say p, and the probability of going left direction is a q, where p plus q is obviously 1. The question is, what is the probability that I will ever reach to 1 again? Starting at 0, what is the probability I will ever reach to 1? Well, my first question is, what if p is greater than or equal to 1/2, for instance? We already calculated the case where both of them are 1/2, right? When p and q are both 1/2, there's with 100% chance we will reach 1. So what if p is greater than or equal to 1? Does everyone agree that, yes, does everyone agree we will definitely reach 1? Do you guys agree? It is common sense, right? Because p is greater than 1/2. Even when p is 1/2, we definitely reach 1. So when p is greater than or equal to 1/2, we will certainly reach 1. Then, so when p is greater than or equal to 1/2, then x is certainly equal to 1 again. The question is, what if p is less than 1/2? Meaning, what if q is greater than 1/2? So what if this is a loaded dice? And it's more likely that, for instance, maybe this is 60%. There's a 60% chance we will go make a left, 40% chance of making a right. So then what is the probability of ever reaching 1? Do you think it is still 1? After a while on these type of random processes, sometimes intuition no longer works. So basically what I'm saying is the following. Suppose that we can, do you want to dramatize the situation? Suppose that someone is holding a gun on you and he's telling you that he gave you a loaded dice or even a fair dice. Suppose that you are right here. You are one step away from the cliff, after which you will die. You're standing right here. Well, suppose that it's a fair coin. If you flip, 1/2% chance you will fall off the cliff, or 1/2% chance you will get away from the cliff. What did the previous, suppose if it's a fair coin, what did we learn from the previous problem? Will we fall off the cliff from the previous problem? So this is 0, 1. -1, -2, we will fall off. But there's a question we didn't address in the previous one. What didn't we address? We will certainly fall off the cliff. It's like Socrates is mortal. You are mortal, yes, you will certainly fall off the cliff, but we didn't calculate something. What is it that we failed to calculate in the previous question? Yes, we will die. Oh, person has an amazing thing, yes. But in average, how long until we die? How long until we fall off the cliff? In average, how many steps? How many times do I flip a coin, right? How many, in average, how many steps until I die? Do you know the answer to this question? What do you think the average is? Do you want to play this game? In average, 1, no, because you will only fall off the cliff in 1 step only if you flip a right. I mean, flip a head. If you flip a tail, then head, then again. Oh, yes. It turns out the answer is plus infinity. So technically, you are not supposed to die in average. And yet, who would like to take this wager? Who wants to play this game? Nobody. Isn't that strange? Okay, let's calculate this later. Okay, so if we have time at the end of today, no, it's not a paradox. We will calculate it. We will in the end, if I have extra time left, I want to quickly show you this. But before that, this problem is more interesting to me. So question 2 or question 2. Oh, this is problem 3, I think, or 2.2. 2.2. This is the second part of question 2. We already showed the question when P and Q are equal to 1/2 each, but now we are distorting the probabilities. It's more likely that we go away from 1. Then what is the probability of ever reaching 1? Ever reaching 1. The meeting ends at 3 p.m. And I have 3 or 4 interesting problems which will drop your jaws. Because this discussion is very deep, obviously, but okay, so don't worry about it. So at the end of the class, I'll give you a couple of resources that you guys can, if you want to learn more about random processes and random walks. So yeah, okay, anyhow, how can we solve this problem? Well, we can pretty much use the same thing, right? Do you want me to walk you through this grid again? I don't want to go through the grid again, right? Q probability a left, P probability a right, Q here, P here. It is, well, okay, if you guys, okay, let me just quickly write it out. Okay, so, oh gosh, this will be torture. Okay, let me just move this away. Oh gosh, okay, well, X, you know what? Because now we have 2 parameters, P and Q. In fact, there's only 1 parameter, right? Q is just equal to 1 minus P. But okay, let me write it like this. Let's write it as XPQ. That's equal to what? Well, with probability P, we will make a right flip and then the game ends. Or with probability Q, we will first make a left and then we will make a right, right? I think it will be Q, sorry, wait. Oh gosh, okay, sorry for that. It will be Q times P squared, right? Do you guys agree? Oops, Q times P. Oh gosh, oh yeah. Okay, please do not request remote control, guys. I can't even write. Someone keeps requesting remote control. Okay, so yeah, don't ask for that. Thank you. I appreciate that. Oh gosh, now that I said it, everyone wants a remote control. Okay, no more remote control. All right, Q times, okay, I can't write it, guys. Yeah, thank you. All right, so this is Q times P squared plus Q squared times P cubed. If you walk through that grid, I don't want to walk, well, oh, sorry, Q squared, there are 2 different ways here, right? 2Q squared times P cubed. You would end up getting this, sorry, 5 times Q cubed. If you walk through the grid, right? Q cubed times P to the 4 and so on. Do you guys agree? So that's a 5, sorry for that. That's a 5. All right, but obviously this is hard to calculate this. I don't want to calculate this. Instead, let's directly use the tool, like the method that we developed, right? So we start here, so at 0. So either we are lucky, with probability P, we reach 1, or with probability Q, which is 1 minus P really, we reach -1. So therefore, the desired thing is equal to what? The desired thing is, oops, let me just move this aside. Okay, just give me a sec. Well, okay. What is it? So if the desired probability is X, so how can I calculate X? Or if you guys want, like I did here, I can use this notation. That's okay. So X will be equal to, well, with probability P, I will reach 1. Or with probability Q, what will happen? How many? I'm now 2 away from 1. So therefore, it will be P squared. Sorry, X squared. Do you guys agree? The probability, first I need to go from -1 to 0, which is the same probability, which we decided to call it as X, to reach to from 0 to 1. So the probability, once you are at 0 to go to 1, which is 1 away from you, is the same thing as the probability from going from -1 to 0 first, and then from 0 to 1. So that's why I put an X squared. Aha. And now we can solve this. So how do I solve this? Quadratic, yes. Let's quickly go ahead and solve this quadratic. I'm assuming everybody knows the quadratic formula. So we have qx squared minus x plus p is equal to 0. So that quadratic. And then, well, that's equal to what? Using the quadratic formula, okay, I'm going fast. So it would be 1 plus or minus square root, what? -1 squared minus 4 times p times q, all divided by 2q. Do you guys agree? And then, okay, so let me move up a little bit. Hey, I can replace q with 1 minus p because p plus q was 1, remember? Replacing it with 1 minus p and working through the algebra. Okay, let me quickly do it. So plus minus the square root of 1 minus 4 times p times 1 minus p, all divided by 2 times 1 minus p. All right, so let me just go this direction. 1 plus or minus square root of what? So this is just 4p squared minus 4p plus 1. But 4p squared minus 4p plus 1 is just 2p minus 1 squared. Aha. All divided by 2 minus 2p, or 2 times 1 minus p. Let's just leave it like this. 2 times 1 minus p. And this thing is simply equal to, well, that we know exactly. So it just comes out of the square root like this, all divided by 2 times 1 minus p. And now we have two cases, either a plus sign or a minus sign. In the case of a plus sign, we get 1 plus 2p minus 1, all divided by 2 times 1 minus p. Or in the case of a minus sign, 1 minus 2p minus 1 divided by 2 times 1 minus p. Aha. And the first case will give us 2 times p over 2 1 minus p. So the first case is just p over 1 minus p, or you can just call it p over q, if you will. The second case will give us what? 2 minus 2p over 2 minus 2p, and that's a 1. Holy cow. Which of them is the correct one? We have two answers. Some of you at the beginning, remember, you said that with 100% chance we will get there, versus some of you said that, no, it can't be 100%. So intuition, going back to the original question. Okay, what was the original question? Yes, we start here at 0. And if q is more than p, that's the interesting case for us, right? So if q is greater than, well, actually, you know what? If q is less than p, we already solved the question. If q is less than p, then we already know what the answer should be. Then the answer is yes, x is better be 1. So we will certainly we will reach 1. But when q is greater than p, we are kind of suspicious that maybe it is this one which is the correct answer. How can I know with certainty? Well, like so many times, a strategy which helps us a lot is symmetry. I'm going to employ symmetry now. Are you guys ready? This will blow your mind. It is counterintuitive. The answer is not 1. This is a false answer. The answer is P over Q. Okay. Let's do it. So the symmetry, yes, is the following. Let's calculate XQP instead. So the probability of going a right move is Q, and the probability of going left is a P. All right. So then that would be equal to Q plus P times Q squared plus 2 times P squared times Q cubed plus 5 times P cubed times Q to the 4 going all the way to infinity. How are these two quantities related? Do you guys see these two equations are related? How are these two equations are related? Yeah, we already solved this, but we have doubts. We are not sure which of the two we should pick. And somehow you are, I mean, I claim that this is not the answer. This one is the answer. When Q is greater than P. That's what we are trying to figure out. Notice that if I were to multiply the first equation by Q, and the second equation by P, they would be equal to each other. Do you guys see that? So I'm multiplying the first equation by Q. Q times X PQ is equal to P times X QP. So that's pretty cool, right? QP. Aha. Now wait a second. We are now looking into the second case. This case. In this case, when Q is greater than P, hey, we already did it, right? X, so let me write it out here. X PQ here is equal to 1 whenever the first component is greater than the second component. But wait, we are in this case now, where we are saying that this component, the first component, is greater than the second component. Hey, that thing is equal to 1. Holy. So as a result, XPQ is just equal to P times 1, which is just P over Q. Move that Q to the right-hand side and done. All right, so now, you know what? I'll go one step further. Let's graph it. P, so the desired probability X came out as P over 1 minus P. So basically, you have the following. So 1, so if, all right, so let me see. If P, so we want to see, so this is the P axis, and this is the X axis, the XPQ axis, right? So the desired probability, like what is the probability that we will ever reach 1? Well, whenever P is greater than 1/2, meaning it's a loaded coin, and it's more likely you will hit the right side. So this is 1/2. We will definitely reach 1 for sure. Oh, sorry. We will definitely reach 1. So this one is definitely 1. But whenever it is less than, it's between 0 and 1/2, meaning the coin is loaded and it's more likely we go to the left side, we need to draw this picture. X of P is equal to P over 1 minus P. It turns out it gives you something like this. One way is just check 1/4, for instance. If P is 1/4, 1/4 over 1 minus 1/4, so 1/4 over 3/4 is 1/3. So this one is a 1/3. I think this is more or less reasonable. So wow, so if you are given a loaded coin, then, and that's basically the solution to this really interesting problem. Now, let me challenge you one step further. Let's see if you understand the main logic of setting up this equation. Okay, are you guys ready? What if, okay, here we go. I'm again on the real line. I have a frog, or you are on the real line. 0, 1, 2, minus 1, minus 2. So at every point we flip a coin. If it comes head, we make, with 1/2 chance, we make 1 step to the right. But then with 1/2 chance, we go 2 steps to the left. The question is, what is the probability that we will ever reach this point, 1? All right. Do you guys, does everyone understand the question? So this is problem 4. Okay, let's solve this problem. You guys set up the equations, okay? So if I flip head, I make 1 right. If I flip a tail, I make two left, not one by one. So we go two left. The question is, what is the probability that I will ever reach the point 1? We can just set up the equation, right? Let's call this probability as x. So how can I set up this equation? With 1/2 chance, I will go to 1 and the game is over. Plus, with 1/2 chance, I will go to that point -2. How far away is -2 from 1? How far away is -2 from +1? Yeah, it's 3 away. So the probability of going from 0 to 1, if it's x, the probability from going from -2 to 1 better be x cubed. Believe it or not. Let me give you a few minutes. This thing will have 3 real roots, and let's see who will see the correct real root. Let me give you a few minutes to solve this one. So can you solve the roots of this equation? All right, this is a cubic equation. Don't try to be a hero. Don't use the cubic equation formula. 2x is equal to 1 plus x cubed, meaning x cubed minus 2x plus 1 is equal to 0. I need the 3 roots. What's the good news? The bad news is, in general, cubic polynomials are hard to solve. The good news is this one doesn't have an x square in it. So you can actually use the Cardano trick if you want no x square. So you can actually use the Cardano trick to reduce it into a quadratic and solve it, actually. But we don't even need that. Okay, good, Justin, amazing. Okay, so some of you guys were doing hard work. Yes, one of the roots is actually 1, plug in 1, it works. So it's possible to factorize this. Okay, so x, now that I know, yeah, Justin mentioned the answer. So what I can do is, all I need now is the coefficients of the second one, which turns out to be what? I think it's x squared plus x minus 1, is that correct? So therefore, we have one solution, which is x equals 1. Oh gosh. So with certainty, we will reach 1. Holy. Now, again, we will go to this philosophical question in the end, right? Which of these 3 solutions is the correct one, right? So that sucks. In the previous question, we were lucky. Because I used the symmetry trick. Will there be a trick like that here? And here, the solutions to this one is, if you use the quadratic formula again, what comes out? So -1. Plus minus, okay, so let's first use the -1 here. So -1 minus square root of 1, is it 5? 5/2. And the last one is -1 plus. You see, I'm a good guy. Look, the second one is negative. The real root here is negative, so ignore this. This one is negative, so you can ignore it because this can't be a probability. So the answer is, again, holy. Are we gonna reach 1 with certainty under these circumstances, or what is this number here? This comes from the golden ratio, right? This is psi, not exactly phi, but this is really it's twin psi, 0.618. So which of the 2 do you think is the answer? 0.618 or the answer 1? Let's vote it out. Yeah, the answer is psi. Yeah, this is a troll. Yeah, this one is not correct. The correct answer is this one. Yep. Sorry for that. Sorry to disappoint. This is not the answer. It turns out to be this one. So you need to find a clever way to convince yourself why this is the one. So in the previous question, like I said, what I did was to utilize symmetry as a trick. If you want, you can utilize symmetry in this one as well. Or some other ideas. Okay. Okay, so can we go back to finally that question that I skipped? So the last problem for today, problem 5, I think it is. It is that, so again, back to the original question. So 0, 1, minus 1, sorry, what am I doing? 2, minus 1, minus 2, and so on. Okay, we start at 0, 1/2 chance we go this way, 1/2 chance we go that way. The question is, we know with certainty we will reach 1, but in average, how many steps does it take in average? How long until I reach 1? I will reach 1 with certainty, I know that, but in average, how many steps? Expected number of steps. First, I want to make sure, well, okay, so let's do it. So the expected number of steps to move 1 in the right direction. So do you guys agree what that index means? E1 means going 1 step to the right, being able to reach the right guy is equal to, well, with what? With 1/2, well, okay, let's solve the general case. Okay, let me solve the general case rather than the 1/2, 1/2. So let's call this P and Q. All right, because remember the 1/2, 1/2, the answer is infinity. Do you want to solve the infinity case first? Oh, okay, let's just call it P and Q again, where Q is 1 minus P, right? All right, let's do it. E1, with probability P, we will make a right move, but it took us exactly 1 step. Or with probability Q, we will make a left move, after which we wasted a step. And what is even worse, we are now 2 steps away from achieving our goal. Our goal is to reach 1. Do you guys see that? So then now the question is, what is E2? How in the world will I come up with E2? Well, the good news is we can use the same logic that we did previously. If the number of, let's think about it. So if the number of steps it takes to go from 0 to 1, in average, if it takes E1 steps, then from 1 to 2 will take us another E1 steps. Do you guys agree that this is just 2 E1? Is it reasonable? So therefore, E1 is just P plus Q plus QE2, which E2 I can replace it, oh well, P plus Q is just a 1, obviously, plus Q times E2, I will replace it with 2E1. Aha, and moving things around, so I will get E1 finally is equal to 1 over 1 minus 2Q. Now I need to make a couple of observations here. If you guys want, I can replace that 1 with P plus Q in the denominator. Replace that 1 with 2 plus Q, and then I have minus 2Q. So that will give me 1 over, I think this way is better to kind of, P minus Q. Holy, look at that. So let's go back. Let's see if it passes the smell test. If P and Q are both equal to 1/2, how many steps does it take in average to go 1 step to the right? Yes. So E1 under those circumstances is 1 over 1/2 minus 1/2. And that's infinity. Wow. So interestingly, if the dice is loaded and if Q is greater than P, then this will never happen. So this will definitely be infinity. Do you guys agree? So obviously the things will get even worse if Q is greater than P. So if Q, oops, what did I do here? Okay, I messed up. Sorry for that. Somehow oh, there you go. Okay, so if obviously, if Q is greater than P, then E1 is definitely greater than, I mean, it's still infinity, right? But we wonder if Q is less than P, right? That's the interesting case. So for instance, if the probability of a right move is, let's say 2/3, and the probability of a left move is 1/3, then suddenly E1 ends up being 1 over 2/3 minus 1/3. So in average, it will take us 3 steps. In average, 3 steps to reach 1, basically. So that's pretty good. So now, in fact, we can even extend this even 1 step further. Guess what? So let me just, so we can make use of this thing. So we can generalize it. EK, starting at 0, reaching to the kth number, so to the number k is just k times E1. So this implies that EK is equal to k over P minus Q again. Aha, and we will only use this if P is greater than Q, and otherwise it is infinity if P is less than Q, less than or equal to Q. Oh, okay, so well, we can go even further. But I'm assuming you guys are probably exhausted by now. Do I want to go further? No, I'm checking my notes. Yeah, I have a couple of additional notes, but I think we went a lot far. In the meantime, I can give you a couple of good references. I think the best classical book, it's hard to read, especially if you are high school. Okay, only high schoolers can read this book because otherwise it's a difficult book. It's available on Google if you search it, a PDF edition. Feller, this guy in 1968, he has this book called Introduction to Probability Theory. But it's an advanced book. It's a university level book, Introduction to Probability Theory. So that's a very good book. If you want, in this book, chapter 3 and 14 is dedicated to these random walks. So chapter 3 and chapter 14. But there's obviously a lot of sources. This is significantly advanced book, obviously. Only read this if you are high schooler or above. If you are middle schooler, don't even bother reading this book. Yeah, if you are 7th or 8th grade, just focus on your math count skills. Another good book that I benefited today was Sheldon Ross. He has two very interesting books. The first book is Introduction to Probability Theory, which is the easier book. But the second book is the advanced book. It is random processes. So he has Introduction to Probability Models. And he talks extensively about Markov chains, which is random processes like this, random walks, and so on. Wow, you're 4th grade? Okay, so definitely don't read this book. Yeah, only if you guys are high school, you guys can, if you guys want, you can go further and look into those more advanced stuff. But more and more in AIME and in AMC10 and 12, we see these type of questions where we attack the problems using pretty much the same ideas. Namely these, what do we call these diagrams? We call them state diagrams, right? So this has become very popular in recent years, state diagrams. So be prepared. So in the last 5 years, there has been multiple AIME, AMC 10, 12 questions, which makes use of these state diagrams. Okay, so last 3 minutes, let me ask you the question of next week. Not next week. On Thursday, I have a combo class with the free combo class again. So if you guys are joining that next Thursday class, we will be attempting this problem, and I'll let you guys go. So the problem I want you to think about is what's called as the gambler's rune. So you should be able to find it on the web if you want. Problem 6, gambler's rune. The question is the following. There's 2 of you. Let's see, me, I have $10 in my pocket, and you have only $5 in your pocket. And we keep flipping coins. Whenever it comes head, you give me $1. So I just focus on me, right? So whenever it's head, I earn $1, and you lose $1. And whenever it's tail, I lose $1, and you win $1. Do you guys agree? This is the effect of these. And we keep repeatedly flipping coins. So after each step, so for instance, if the first one comes out tail, then you will be at 6 and I will reduce to 9. The question is, what is the question? What is the probability that I will run out of money, right? Probability I will run, or my opponent, doesn't matter, out of money. I will bankrupt. That's it. So that's the question. And if you guys are really good, you can even ask a harder question. In average, how long until one of the persons will run out of money? In average, that's the harder question. So question 1, question 2, in average, how long until one of us run out of money? Run out of money. One of us running out of money means the game is over, right? Because the other guy doesn't have money. Why would the other guy play with him, right? All right, that's it. So Gambler's Run, you can search it on Google, Wikipedia, wherever you want, AOPS, and have fun. So I'll see you guys on Thursday, 1:30. Feel free to sign up and join our session again. Thank you, everybody.